Hello, it's good to be with all of you again today. Today we're going to be talking about the dot product. So this is section 12.3 on the dot product and the dot product and its many uses. So unlike numbers, there are two ways to multiply vectors. We're going to learn about the dot product here, that's the first of those methods, and the cross product in the next section. So here's our definition. If the vector A equal to A1, A2, A3, and the vector B is equal to B1, B2, B3, then the dot product of A and B is the number written A dot B given by A dot B equal to A1 B1 plus A2 B2 plus A3 B3. Notice all that's happening is we are taking the components of A and multiplying them by the components of B. All the A's are getting matched up with all of the B's. So important note here, the result of the dot product is a scalar, it's a number. And so every time you're working with dot products, you better end with a number at the back end. Sort of one of those things that we get to remember. Example 1, if we want to find the dot product of 1, -2, -1, and -6, 2, -3, then we will take 1 times -6 plus -2 times 2 plus -1 times -3. In color, that's the sum of all of these little products. And notice that we're pairing up the first components, that's these two. We're pairing up the second components, that's these two. And we're pairing up the third components, that's those two. Okay. Example 1b. Here we've written our vectors using the ijk notation. So we have a half I plus 3j plus k dotted with 4i minus j plus 2k. Same exact deal. So we'll take all the components of the first vector and dot them, multiply them by all the corresponding components of the second vector and add. So half times 4 plus 3 times -1 plus 1 times 2. So this is the yellows dotted with the greens. And once again, we're taking the coefficient in front of the i's, that's the half times the 4. And then we are looking at the coefficients in front of the j's, that's the 3 and the -1. And the coefficients in front of the k's, that's the 1 and the 2. So we take all those little products and we add them together. The dot product obeys many of the laws that hold for ordinary products of real numbers. These are stated in the following theorem. So you'll notice that A dot A is the magnitude of A quantity squared, kind of like you would think. A magnitude is a square, is already a scalar, so we square it, it stays a scalar. A dot B plus C equals A dot B plus A dot C. 0 dot A is 0. Notice that this 0 is 0 vector. This 0 is 0 scalar. And then property 2, A dot B is equal to B dot A. And property 4, scalar C times A dotted with B is equal to C, scalar C times the product A dot B, or A dot scalar C times B. All of these work kind of the way you would expect them to work. And once again, I would say you probably don't need to memorize the properties of the dot product. The key is to remember that the dot product is intuitive. It operates the way that you would expect it to work. Of the things that are here, the one property that will get used repeatedly that might be worth memorizing is this very first one, which gives us a relationship between the dot product and the magnitude. And I think it should be intuitive. If you just think about property 1, if you had the vector a dot a, so a1, a2, a3 dotted with itself, a1, a2, a3, then that's going to equal a1 squared plus a2 squared plus a3 squared, which should remind you of the magnitude of a vector, except for there's no square root, right? Why? Because we squared it, and that square killed the square root. So moving on. We can easily prove these properties. Some of the proofs are in the book. We're not going to go in too far. So there is an equivalent geometric definition that physicists usually use as their starting place. And you can show that these are equivalent using the law of sines. So for the physicists, they have, if you have, let me make sure I have my lettering right. If you have vector A and vector B, and theta is the angle between them, then A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So here's a relationship between vectors and angles. So this is formalized in the next theorem. So if theta is the angle between vectors A and B, then A dot B is equal to the magnitude of A times the magnitude of B times the cosine of theta. Note that this last theorem gives you a corollary. And the corollary is that if theta is the angle between the non-zero vectors A and B, then the cosine of theta is equal to A dot B over the magnitude of A times the magnitude of B. So let's do an example where we use this corollary. So if we want to find the angle between A equal to I minus 2j minus 2k and B 6i plus 3j plus 2k, then we can find the, we can start by finding the dot product of the two vectors. So we know that A dot B is going to be equal to the yellow one dotted with the green one, which would be 1 times 6, or 6, plus negative 2 times 3, negative 6, plus negative 2 times 2, negative 4, which is a funny way of writing negative 4. We can find the magnitude of A. So the magnitude of the A vector is going to be the square root of 1 squared, or 1, plus negative 2 squared, which is 4, plus negative 2 squared, which is 4. Altogether, that's the square root of 9, which is 3. And the magnitude of B is equal to the square root of 6 squared, which is 36, plus 3 squared, which is 9, plus 2 squared, which is 4. And all this is the square root of 49, which is 7. So this together tells us that the cosine of theta is equal to negative 4 divided by 3 times 7. Or the theta is equal to the arc cosine, the inverse cosine of negative 4 over 21, which is, remember, that's the exact answer. But if I wanted this approximately, I can make sure that my calculator is in radian mode. That's always my default. And find the arc cosine of 4 over negative 21. And I get 1.76 approximately. And that would be radians. So a teacher story. So remember that application about the roof? Well, me, one of the authors of these notes, learned this the hard way. So I was sheeting a new roof that was putting new wood down under the roofing material, and I needed to cut some angle pieces. Being a smart mathematician, I used my trig skills. My result was close, but not quite right. The boards didn't fit. So out in the real world, I couldn't figure out how to do this angle in 3 dimensions. So I did what most people do. I got close, and then I used a lot of nails and kind of held the board in place. So I later told an engineering friend about this, and my friend said, "Why didn't you use vectors and dot products?" Lesson learned. So let's see if we can figure out how we could have done this same question with vectors. And again, looking at the picture, what I was trying to figure out was the angle between here in the valley and the straight up part. Like what's this? What's that angle there in the valley that I needed to cut my board at? That's the real picture. That's what it really looked like when I was working on it, including those bad boards that I got. So suppose one plane of a roof has a 612 pitch, and it's intersected by a second plane that has a pitch of 412. Find the angle between the valley and a line going straight up the 612 roof plane. So we need 2 vectors. So the first vector we need is going straight up the roof plane. So the first one, straight up the roof. And this is going to be here, straight up the roof. Maybe we'll call it vector U. And we know we've got a 612 pitch. It doesn't matter whether we go in the X direction or the Y direction. So maybe we'll start with the X direction. So we know our run is going to be 12 because it's always 12. We know we're not going to go anywhere in the Y direction. And vertically, we're going to go up 6. So there's that 612 pitch that we talked about earlier. And then we need a second vector that goes up the valley. Okay. So we notice that if we go, so this is our V vector, maybe V for valley. So if we go 12 in the X direction up the valley, we know that we're going to go 6 vertically, same 6. But if I went, in order to go 6 up the other direction, I would have had to go 1.5 of the other 12s. Thinking about it this way, that 412 is if 4 is to 12 as 6 is to what? So we need this. Oh. We need to know what that Y value is. And so we can, like we found earlier, the Y value there would be 18. And so now I have my 2 vectors. If I want to find the angle between, I can use the formula that we used before. So we need to find U dot V. That's going to be 12 times 12 or 144. Plus 0 times 18 is 0. Plus 6 times 6 is 36. We need the magnitude of U, which would be the square root of 144 plus 0 plus 36. We need the, or I wouldn't normally use decimals, but we're actually talking about real life here. We're talking about actually cutting boards. So maybe we'll find decimals for this particular example. So this is a, oh, this is actually a perfect, oh, this is a plus. My bad. So about approximately 13.42. And the magnitude of V is going to be the square root of 144 plus 324 plus 36. Which is approximately 22.45. So the angle that we're looking for is approximately equal to the arc cosine of that dot product, which I guess is 180, divided by 13.42 times 22.45, which now usually I'll be in radians, but since when we're actually doing work, you know, with saws and with wood, we work in degrees. So I'm going to switch back to degree mode. And here our angle is going to be 180 divided by quantity 13.4 0.42 times 22.45, and I've got, which is approximately equal to 53.31 degrees. So the question is to find the angle between the valley and the line going straight up that 612 pitch. So here's the angle in the valley. Vector 2, vector 1, straight up the roof, and the angle that I need to cut things at is 53.31 degrees. Oh, if only I had had vectors back when I was building this particular project. Two non-zero vectors A and B are called perpendicular or orthogonal. It's our key term. If the angle between them is pi over 2. Notice we could also say 90 degrees, but the focus of this class is on radians, as that's the prevalent measure used throughout mathematics. Now we can calculate the dot product of the perpendicular vectors as follows. So A dot B is equal to the magnitude of A times the magnitude of B times the cosine of pi over 2. And I'm hoping you remember that the cosine of pi over 2 is 0. So, oh my gosh. Conversely, if A dot B equals 0, then the cosine of theta equals 0. So theta equals, again, pi over 2. Note that the 0 vector is considered to be perpendicular to all vectors. So it's okay if A is 0 or B is 0. Therefore, we have the following method for determining whether two vectors are orthogonal. Two vectors are orthogonal if and only if A dot B equals 0. This is important. Let me repeat it. Two vectors A and B are orthogonal if and only if A dot B equals 0. So if you want to find if vectors are perpendicular, use the dot product. Anything that has to do with perpendicular or orthogonal will somehow tie to the dot product. The dot product eats perpendicular vectors for lunch. So let's do an example of this. So if I want to show that vector A, the yellow one, and vector B, the green one, are orthogonal, I will find their dot product. So if this is A and B, then A dot B is equal to 3 times 0 or 0 plus negative 2 times 2 -4 plus 1 times 4, or 4, which is equal to 0. So what we're saying is, since the dot product is 0, the vectors are perpendicular. Because the cosine of theta is greater than 0, if theta is between 0 and pi over 2, and the cosine of theta is negative if theta is between pi over 2 and pi, we see that the dot product is positive for thetas less than pi over 2 and negative for theta greater than pi over 2. That is, we can think of A dot B as measuring the extent to which A and B point in the same direction. The dot product AB being positive, if A and B point in the same general direction, it's 0 if they're perpendicular, and it's negative if they point in exactly the opposite direction. Here's the picture. So if A and B point in roughly the same direction, then the dot product is positive. If A and B are perpendicular, then the dot product is negative. If A and B sort of point in opposite directions, then the dot product is negative. In the extreme case where A and B are point in exactly the same direction, we have that theta equals 0, so the cosine equals 1, and A dot B equals the magnitude of A times the magnitude of B. If A and B point in exactly the opposite directions, then theta equals pi, cosine equals -1, and A dot B equals negative the magnitude of A times the magnitude of B. Direction angles. The direction angles of a non-zero vector A equal to A1, A2, A3 are the angles in the interval 0 to pi that the vector makes with the positive x, y, and z axes. The cosines of these angles are called the direction cosines. Note, this is a topic that may be needed for the homework, but direction angles are not used heavily elsewhere in this class. So you probably don't need to memorize this for a test, for example. So let's look at the given picture. Direction angles. The direction angles of a non-zero vector A equal to A1, A2, A3 are the angles in the interval 0 to pi that the vector makes with the positive x, y, and z axis. The cosines of these angles are called the direction cosines. And there's kind of a cool connection between these direction angles or direction cosines and unit vectors. And so this is a little bit of a side topic. The topic may be needed for homework, it may be handy, but these are not generally used heavily in calculus. And so this is something to enjoy, but not necessarily something to memorize. So let's dive into direction angles and direction cosines. So let's start by looking at the picture. So if we have a vector A here, then we would describe the direction angle made with the x-axis as alpha. Okay, and you'll notice we can represent alpha, or sorry, the positive x-axis, by just looking at the I vector, which is 1, 0, 0. And so if we want to find the cosine of alpha, we can use the formula from earlier in the dot product. And so notice when we take A dotted with I, most of this stuff is going to disappear except for the A1 times the 1, which is just A1 over the magnitude of the A vector. And then if we want to find the beta vector or beta angle, that's going to be from the positive y-axis up to the vector. Here's our B for beta. And to find that angle, we can dot A with the j vector, the vector unit vector along the y-axis. Notice there's our j vector, and it's 0 everywhere except for the middle component. And so our product is going to be A2 over the magnitude of A. And thirdly, if we look, we're looking for the gamma direction angle. That would be the angle from the positive z-axis down to the vector. So here we could dot A with the k vector, which is 0 everywhere except for in the z component. So at the end of the day, all that's going to show up is A3 over the magnitude of A. So this gives us the following formulas for A1, A2, and A3. So A1 is going to be the magnitude of A times the cosine angle in the x direction. Then A2 is going to be equal to the magnitude of A times the cosine angle in the y direction. And A3 is going to be the magnitude of A times the cosine angle in the z direction. So remembering what the vector A is, so here's our A vector, it's equal to A1, A2, A3, but now we have a formula for that. So here's our A1 component, got a little frisky, our A1 component, our A2 component, and our A3 component. So there's a new representation for A. You'll notice that there's a common factor of magnitude of A throughout. And so we can pull that out front. And so now I have vector A is equal to the magnitude of A times a vector made up of all of those cosine angles. And I can divide through by that magnitude of A, giving me A over magnitude of A equals cosine of alpha, comma cosine of beta, comma cosine of gamma. Notice the thing on the left is a unit vector. So on the right, we see the cosine alpha, cosine beta, cosine gamma, and we can basically find the dot product of this thing with itself, okay, or find the magnitude of the vector squared. And so here you have the cosine alpha squared plus cosine beta squared plus cosine gamma squared. Now remember, this is a unit vector. And so since it's a unit vector, we can work through all this algebra. You can think about it as A1 squared over magnitude of A squared plus A2 squared over magnitude of A quantity squared plus A3 quantity squared over magnitude of A quantity squared. Combine the like terms. You could write out everything in terms of radicals and squares. But the key is that this vector is a unit vector. And so when we're trying to find a unit vector and we working with a unit vector, and if you take this sum of those squares of those terms, then you are definitely going to get 1 out the back end, right? The length of the unit vector equals 1, and or maybe you could say it equals the square root of 1. And if we get rid of that square root, because there's no square root in this formula, then you're certainly still going to end up with a 1. Example 5. Find the direction angles of the vector A equal to 2i plus j plus 4k. So my first step is going to be to find a unit vector in the direction of A. So my unit vec is going to be A divided by the magnitude of A. And my magnitude is going to be 1 over square root of 4 plus 1 plus 16. 2 squared plus 1 squared plus 4 squared, square root of 21, times 2, 1, 4. Okay. And this tells me that this must be equal to the cosine of alpha, cosine of beta, cosine of gamma. And so my first direction angle alpha is going to equal the arc cosine of 2 over root 21, which is approximately what in radians? Arc cosine of 2 divided by square root of 21. 60. Ooh. I'm still in as a degrees. 1.12 radians. Okay. Beta will equal the arc cosine of 1 over square root 21, which is approximately 1.35 radians. And gamma is equal to the arc cosine of 4 over root 21, or 0.51 radians. So let's think about the vector v equal to AB in 2 dimensions. So we say that A is the horizontal component of V. We could also say it's the component of vector V in the direction of the x-axis, or onto I, or any vector in that direction. So we could write this as A equals the component of V in the I direction. We could also call AI the shadow of V onto the x-axis. In correct mathematical terms, AI is the projection of V onto I, and it can be written as A times vector I is equal to the projection of V onto I. Just to be clear, this top one, the A equal to the component of V in the direction of I, this is a scalar. And A times I equal to the projection of V onto I, this is a vector. We can define component or projection of a vector onto another vector or any other direction. And so there's some formulas coming. Let me show you this animation before we get too wild and crazy. So here's how this works. So if I want to look at the projection or the shadow of vector A in the direction of V. And so notice that if they're running in roughly the same direction, that vector U projects onto the shadow of vector V. So that would be this projection of U in the direction of V, or this OP. And the formula for it would be the magnitude of U times the cosine of theta times V over magnitude of V. That it's going to get bigger the closer they are together, because the cosine of a small angle is close to 1, and still going to be it's going to be a vector, because we have this V over magnitude of V that gives me a unit vector in the V direction. If they're kind of pointing opposite directions, then the angle is going to be bigger than pi over 2. In other words, this cosine is going to be negative. So you've got this magnitude of U times a negative number. And then we know the direction it's going because you have the V times, or V over magnitude of V, the unit vector in the V direction. If they happen to be perpendicular to each other, you'll notice that the theta is pi over 2, cosine is 0, and so your vector projection is basically the 0 vector, because they're not going anywhere. In this particular animation, I write the scalar of U in the direction of V. In the book, we use the component notation, so they would say component instead of scale, same thing. And here, all it is the length the length of this vector. So that's this scalar part. So it's the same picture, but here we're talking about the length of the vector versus the actual vector itself. Okay. So just to say this again, the projection is sort of the vector shadow onto in the v direction of vector u. The scalar or the component of u in the direction of v is just the length of that shadow. So let's see if we can derive the formulas for this, for these ideas. So as we talked about with the animation, if your vectors are roughly in the same direction, then that projection is of B onto vector A is kind of a shadow vector along A in the same direction. If they're going in opposite directions, so A is going in that direction, B is going in this direction, then the projection would still be the shadow of B in the direction of A. It just happens to be pointing in the opposite direction as A. Similarly, the scalar projection of B onto A, also called the component of B along A, and you noticed on the animation that it used the scale abbreviation. Here we use the comp abbreviation. Same thing. Is denoted by the component of B in the direction of A. It's just defined to be the signed magnitude of the vector projection, or magnitude of B times the cosine of theta. Okay, and it's literally, it's the length of this shadow. It's the length. Notice there's no arrow. So it's a scalar, no arrows. In the picture. Right here. Okay. So let's see if we can see a simple derivation. So the component of B in the direction of A is equal to the cosine of theta times the magnitude of B. So, and notice the cosine of theta, we can take this cosine of theta and we can say, well, the cosine of theta could also be found using A dot B over the magnitude of A times the magnitude of B. But notice there's a magnitude of B up here and a magnitude of B in the denominator. Those cancel. And so we get a nice friendly formula for the component of B in the A direction. This particular formula comes up a bit over the course of the class. And so this is a maybe memorize. You definitely want to understand. Maybe memorize. If you're taking physics or engineering, you probably will use it quite a bit. And so it probably is worth memorizing. Continuing on. Once we have that component of B in the A direction, then we can figure out what's the direction that we want it to go. So here's that same A dot B over the magnitude of A. And if I multiply it by a unit vector in the direction of A over magnitude of A, then that will give me the projection of B in the direction of A. And so combining like terms, you get this nice formula at the back end. The projection of B the projection of B along A or onto A is A dot B over the magnitude of A squared times vector A. Once again, the top one is a scalar, represents the length of the vector. the bottom one is a vector, and it's kind of the top one's the length of the shadow. The bottom one is the shadow, but it has a vector, a direction to go with it. So notice the vector projection is the scalar projection multiplied by the unit vector in the direction of vector A. Let's do an example. Example 6. Find the scalar and vector projection of A equal to 6i plus 3j plus 2k onto B equal to I minus 2j minus 2k. So we're going to use the formulas that we've just been given. And so first we're looking for that scalar projection. So this is the component of A in the direction of B. And our formula for this is that this will be equal to A dot B divided by the magnitude of vector A. So A dot B will be, let's see if we can color them. So this is going to be A dot B, which would be 6 times 1 or 6, plus 3 times negative 2, so that's minus 6, plus 2 times negative 2, minus 4, all over the magnitude of A, which would be the square root of 36, plus 9, plus 4. So here we have negative 4 over 7. So this is the component of A in the direction of B. Maybe you could think about it as the length of the shadow. And so the second part asks us to find the vector projection of A onto B. So this would be the projection of A onto B. And to do that, we take the answer above, which is negative 4/7, and then we're going to multiply it by a unit vector parallel to B. Parallel to B. So what would that be? Well, we would know that it would be B, which is 1, negative 2, negative 2, times the 1 over the magnitude of B, which would be the square root of 1 squared plus 2 squared plus 2 squared, or 9. So this looks like it will be negative 4 over 7 times 1/3, comma, negative 2/3, comma, negative 2/3. So notice that at the end of all this, we had a scalar for our component of A in the direction of B, and we had a vector as the projection of A along B. And again, notice that the length of that projection is the same as the component of A in the direction of B, and the vector that part of it, the unit vector we're using, is just made from that B vector. Let's talk about one last application of the dot product in this section. So the work done by a constant force F that moves an object from P to Q, which creates a displacement vector, can be calculated by work equal to force dot distance. Now you may have played with work in the past, okay, and said work equals force times distance. But what we're doing here is slightly more sophisticated, because we are now allowing the force and the distance to not be perfectly parallel or in line with each other. And so now we're going to use the dot, not the multiply. So note, force and work are major themes in the last part of Calculus 4. So we're talking about it a little bit here. Work might have come up a little bit in Calculus 2, but really what we're doing is we're trying to set things up for Calculus 4 and also maybe a little bit for physics and engineering. Let's look at a manipulate. So in this picture, what I want to point out is that we have some mass represented by the block, okay? And then we can ask ourselves how much of the downward force, the force of gravity, how much of that force is in the direction of the that the block is going to slide. That would be the parallel component. Okay. And how much is going to be perpendicular, kind of like straight into the floor. That would be our normal component. And notice even the way we talked about this sort of helps us to see this idea of angles and projections and components coming into play. Notice that the steeper the angle, the greater the part of the force that's going to be down the slope, versus with a shallow angle, most of the force is going to be coming straight down. It's going to be normal, the normal part, normal to the surface or the inclined plane. Okay. And so again, there's this hint of projections, dot products showing up in the even in the picture, even without having without having gone deeply into the math. So let's do a simple example here. So if the magnitude of our force is 40 newtons and the distance that we are going to travel is 3 meters, and the angle between the two is 60 degrees, we want to find the work done. So maybe we think about this as follows, that we're going to travel a distance of 3 meters. We're going to pull, in order to make this happen, we're going to pull with a magnitude of 40 newtons. Okay. Magnitude of D equals 3 meters. And the angle between these is at 60 degrees. And so the work is going to equal F dot D, or magnitude of F times the magnitude of D times the cosine of theta. So this is going to be 40 times 3 times the cosine of 60 degrees, which is a half. And so the work done will be 120 times a half, or 60 Newton meters. Example 8 is very similar. It says, how much work is done if a man pulls a wagon from point P, -1.5, to point Q, 8.2, by applying 20 pounds on the handle that makes a 60-degree angle with the horizontal. So it looks like we're going to need to find vector PQ, because that's going to tell us about our displacement. So it's going to be position vector in the Q direction minus position vector in the P direction. So 8 minus -1 would be 9. And 2 minus 5 would be -3. And we want to know what's the length of that displacement. Square root of 81 plus 9, or square root of 90. And we know that we are going to be pulling at, we know that the magnitude of the force is going to be 20 pounds. And so we are traveling with along some vector PQ, not to scale. I'm not actually locating my points. I'm not really worried about that. And we're pulling along the handle with some force F, and the angle is 60 degrees. And so we know that our work, so here's our displacement, our work is going to equal F dot D. And like we did before, we can see that this is going to be 20 pounds times square root of 90 feet traveled times the cosine of 60 degrees, which is a half, or when all is said and done, we'll have 10 root 90 foot-pounds of work is done. Thanks. That concludes our lesson on the dot product.